So, okay. So hello, everyone, whoever is connected to the meeting. And I basically would like to thank for the opportunity to give this rather big overview talk. I mean, I wasn't actively in the field of polarization for the last 2 years, but nevertheless, it's my pleasure to kind of go back and review what has been done also recently. So with that, I should go to the next slide. So I start from a little bit far. So let's say the theoretical ideas for the polarization, they evolved. They all basically were revolving around the concept of the initial angular momentum, and I think early works were focused on polarized quarks, which were produced out of the initial rotating system, which would produce polarized hadrons at the end. And I think the next talk in this workshop, which would cover polarization in transport models, would maybe shed some light on that. What is more relevant to my talk is basically the point number 2. So the later developments assumed that, okay, there is, because of the initial angular momentum, there is a vertical fluid which is created, and this vertical fluid then leads to the polarization of the finally produced hadrons. So one of the milestone papers about this concept is basically cited exactly at this point. So again, because the talk is about the hydrodynamic models and polarization, I basically start with the basic formula, which is really the basic formula which is used in all the calculations, and not only hydrodynamic calculations, actually. So the basic mechanism is the spin vorticity coupling. So in this case, one assumes that at the moment when the fluid transforms to particles, not only momentum degrees of freedom are in complete or incomplete thermal equilibrium, but also the spin degrees of freedom are in thermal equilibrium. And this assumption with some math basically leads to the formula which is at the bullet point number 2. So there is a formula which describes the mean polarization, the mean spin of particles which are produced, which reside in the fluid actually. And this mean spin is driven by the gradients of this beta field, so the inverse temperature field. And this formula can be naturally embedded in the Cooper-Frye prescription, which basically leads to the formula which is framed in the black. And essentially, this formula is the formula which is used in all of the calculations. So that formula has two important consequences. So because it's thermodynamics.
So can I ask a question? I'm sorry.
Yeah, sure, of course. Go ahead.
Because this, on the right-hand side, you have this free index mu. On the left-hand side, there is none. Is it contrasted with U?
Yeah, I think so sorry. Okay. I think I missed the free index, the mu index on the left-hand side. So of course that's S mu, which is equal to the
so that's
the expression on the right-hand side. So that's S mu, sorry. Yeah. Okay, and actually the same applies to the formula down. So the S mu depends on the average local S mu on the hypersurface. So there should be mu index in the formula. Okay, so nevertheless, this formula basically leads to two important consequences. So first one is because that's thermodynamics, then the polarization of particles and antiparticles is in principle equal. The only difference can be caused by chemical potential. Then the other consequence is that this polarization effect, different from non-relativistic case, it's caused not only by velocity but also by temperature gradients, because it depends again on the beta field, which involves temperature. So with that, I basically go on for the next slide. then essentially, let's say, looking around the market of these existing calculations, there are two ways to do it. So the first way is to have a hydrodynamic evolution. That's the point number one. And at the moment, at the hypersurface of freeze out, one can basically apply the formula from the slide above and this way calculate the polarization. So that's practically how it's done in all of the hydrodynamic models on the market. The way number two, or the method number two, which is used in transport models, is essentially to have a Parton or hadron cascade. Then at some point one can apply coarse graining, basically mapping the local energy and momentum into the temperature and chemical potential fields and velocity field. And once there are the fields of thermodynamic variables, then one can again use the formula from the slide above. So in principle, that's the way how it's done in many, probably most of the transport calculations. And with that, I basically refer to the talk next Monday because I overstep a little bit my domain here. So with that, I basically go on to list the existing calculations. So in principle, looking at the available hydrodynamic calculations, so far I found 5 of them, more or less, 5 different models. So the first, probably the earliest model which was applied for the polarization business is this so-called PCR, so particle and cell hydrodynamics. I'll discuss those models later in more details. Then the next calculation was done in the EcoQGP by Francesco Bicchettini, Gabriele Ngirami, and many other people which do not fit into the line here. So I just put the dots instead. Sorry for that. Then after that, there was URQMD plus VHLE or Glauber plus VHLE, which was basically done by me with Francesco. Then there are 2 other models. So the AMPT initial state plus CL-VISC, which is yet another viscous hydrodynamic model. And last but not least is so-called 3-fluid hydrodynamic model. So as you can see, all those different models, they because of the way the initial state is constructed and frankly speaking, because of the way the whole model is constructed, those models have slightly different applicability in terms of collision energy. So I would say when it comes to polarization at lower energies, then that's basically either URQMD plus VHLE or PCR or 3FD. So only 3 out of 5 models. Whereas 2 other models were used for the differential polarization studies at high energies, but more about that later. So one important point about all the hydrodynamic calculations is that all of the models, at least that's my general understanding, is that all of the models had been tuned for the basic hadronic observables previously. So the polarization observable is not something which the model is tuned to reproduce, but it's basically something which you get for free from the model. And to my understanding, none of the models were specifically tuned to reproduce the polarization observable. It's basically rather the other way around. So they were already fixed earlier from the basic observables. And here I show let's say the sample result from the URQMD plus VHLE model. So you can see that first of all, you basically tune the model to reproduce the rapidity distributions, the elliptic flow, and then you look at the polarization. The other example comes from the 3-fluid hydro model by Ivanov. So that's the last bullet point from the list of model from 2 slides before. So as you can see as well, the model had been tuned actually, I think, before even 2018. Even in previous works, it's been tuned to reproduce the basic observables. So not only the PT spectra, because I don't want to pollute the slide with different plots, but I think it also works for the elliptic flow, for the directed flow, and then with the tuned model, you can go ahead and look at the polarization observable. So then with that, I basically proceed to the global polarization observable. So the first general expectation, and that's been discussed already at the workshop, and that will be discussed probably many times again during the workshop. So the first expectation is that all the lambdas should be, all the final lambdas which are coming out of the fluid, because of symmetry reasons, they should be polarized along the angular momentum of the system. So here I show two different sketches of the geometry of the reaction. So you basically have, for example, on the right, you have the gray plane, which is the reaction plane. And there is a vector which sticks out of the reaction plane, so the angular momentum J, which sticks upwards. And the expectation is that the polarization of hyperons would be, I think, opposite to this vector, but in that direction, exactly. And in principle, that's exactly how it happens in the hydrodynamic model. So here I basically show let's say the sample results from one of the models. In this case, that's UQMD plus VHLE. Calculation for particular collision energy, 19.6 GeV, so that's in the middle of the beam energy scan range, 40 to 50%, so some non-central collisions, and here you can see on the plots the different components of polarization in the global frame. So there is a component so-called PB, which is directed along the impact parameter, and P longitudinal, or PZ, which is directed along the beam. And you see that those two components, they basically have quadruple structure. Of course, much more on that later, but for now, it's basically just a quadruple structure, which still averages out to zero if you look at the global polarization, right? So then the only component which does not average out to zero is the one on the right. So that's the PJ, or basically a component which is directed along the perpendicular to direction plane, so along the angular momentum of the system. Yeah, so that's that from this slide. And in principle, if you go ahead and calculate the global polarization at different collision energies, so there are so you can basically you can get the results which are described here. So on the right, on the left, there is a result from the UQMD plus VHLE model, and on the right there is a result for the mean polarization of lambda from the PCR model. So first of all, in principle, the results, those two different results, both of them show polarization which decreases. It's not clearly seen maybe because of the scale, but it actually quite strongly decreases as a function of collision energy from, let's say, more than 1 or more than 2% at the lowest energy, down to, let's say, down to less than 1% or even much less than 1% at high energies. So there is a strong decrease of polarization at mid rapidity as a function of collision energy, and this goes along with the data. So you can see that on both plots, the calculations from the model, they reproduce, they are more or less within the experimental error bars for the lambdas. So one thing which I probably think worth to mention is that you cannot really compare those two results from the models directly, because they're calculated with different definitions of centrality. So for the calculation on the left, I basically took the full sampling of impact parameter within the range from 6.7 to 10.4 Fermi. So more or less in the same way as the 20 to 50% centrality class is defined. Whereas on the right, the calculation has been done in PCR model with fixed impact parameter, which is equal to 0.7 times twice the average radius of the nucleus, which roughly corresponds to 45% centrality. So that's basically, I would say, almost the biggest possible impact parameter in the centrality class. So that's a little bit biased towards the towards higher centrality. So maybe that's why the polarization on the left, on the right, is a little bit higher than on the left. And in principle, it's kind of hard to compare them.
Can I ask a question again?
Sure.
Sorry. So just to understand these figures, well, I'm also kind of like new to this field, so I'm not very easy sometimes reading these figures. So the so these triangles are the observed values for lambda and lambda bar polarizations, right?
Yes. Yes.
And so and on the left hand side, when you say model, this is the model calculation, the same model calculation for lambda and lambda bar.
Yeah, exactly. Yes. Yes.
So am I correct that the model is predicting an opposite sign in the difference of lambda and lambda bar polarizations?
Well, okay, that's a good question. In principle, I would say that the models, actually both models, predict almost the same. So this difference between lambda and lambda bar on the left, which you see, it's basically really small, and in principle, yes, there is this small splitting, but I would say that it's basically effect of chemical potential. It's an effect that in the hydrodynamic model, because of baryon chemical potential, the lambda and lambda bar, they're produced at slightly or somewhat different space-time points. I mean, the production is enhanced in certain regions with positive chemical potential and suppressed with negative chemical potential for lambda with respect to anti-lambda. And that creates that creates a slight splitting on the left. On the right, I think on the right, there was, I'm not really sure, but maybe there was even no chemical potential. And in this case, if there is no chemical potential, then the lambda and lambda bar result would be exactly the same.
Right. So, and my next question, on the right, these red dots, they represent the average value of lambda and lambda bar polarization, or?
Well, you can, yes, you can think of that probably as an average value.
Okay.
But you can also say that in principle, if the model is simplified, then you basically get the same polarization for lambda and lambda bar.
I see. Okay. Yeah. Thanks.
So that's.
Iurii, so you're saying that the difference in the lambda and lambda bar polarization in your calculation is just due to baryon chemical potential. Is that because you used, for example, Fermi-Dirac distribution, or?
Yes. Yes. Sure.
Okay, I see.
That's for the lambda. That's a usual Fermi-Dirac with chemical potential, with baryon chemical potential. So actually, to be more precise, that's both baryon and strange chemical potential. But strange chemical potential is much smaller effect, especially at high energies.
Yeah.
So that splitting comes solely from chemical potential. Yes.
So in the kind of AMPT kind of calculation, I just want to point out that actually people usually think that lambda and lambda bar will have the same polarization from modeling like AMPT, but actually a little bit surprisingly, they're not. So in the AMPT, actually you also find that the lambda polarization is slightly higher than the anti-lambda polarization for different reasons. So in there, the reason is because of the timing would be different. So on average, lambda is produced a little earlier than on average than lambda bar. At least that's what we see from the sort of histogram of production. So that lambda pick up a little bit higher polarization. So it may say it's sort of due to different freeze-out time. But anyway, I think from MPT we also see that they are not exactly the same as no energy, and the lambda is slightly higher, which of course is different from the data, which means there's some other source of reason for that.
Well, in principle, I put it on the next slides. So so yeah, that's one of the explanations for the splitting. There was actually the paper by Vityuk, Bravin, and Zabrodin. So that was basically pure URQMD calculation, which is also a transport model. So what they saw is precisely what you said, that lambda and lambda bars, they freeze out in a little bit different space-time regions. And that basically causes, so they showed in this paper, in this first link, in the first preprint, that those different freeze out points, they basically cause different mean polarization of lambda and anti-lambda. And in their case, I think they actually reproduce the experimental trend. So they showed that lambda bar actually has larger mean polarization than lambda. I did not put this slide, I did not put those plots into the talk because that is kind of, again, outside of my subject. So it's polarization transport model. So I hope that will be discussed next Monday more. So
thank you for the information. Yeah, I see. I'll look into that. Yeah. At least from our case, it's sort of opposite to the experimental trend. But yeah, I'll look into that. Thank you.
Yeah, and also there is also, it's basically just to continue the discussion. There is also the last explanation which I put is this recent papers in the so-called core corona picture, which goes a little bit in the same direction as the UQMD calculation, that basically that if you approximate the model, if you approximate the fireball very roughly by core part and corona part, and if you assume that corona only produces lambdas, whereas core produces both lambda and anti-lambda, then this would also lead to larger polarization of anti-lambdas. So that's the second preprint which I briefly cite here. So far those are basically kind of two explanations in the same spirit, I would say, for the splitting. Okay, so with that I move on to the next slide. So since I said that there are basically three models which work for lower energies, that's the third one. So that's a so-called three-fluid hydro. Iurii Ivanov was describing that quite extensively yesterday. Here I can only mention that there is excitation function of lambda polarization also from the 3D. It also roughly within error bars for lambda with experimental data, same as two other calculations essentially. The calculation was also done at fixed impact parameter, so it's a bit smaller than the calculation in the PCR model. So maybe that's one of the reasons why the polarization is also slightly smaller overall. And the other conclusion, actually, what Iurii Ivanov was drawing is that, so he was looking at the whole system, not only mid-repeativity, but also whole system. And he was basically also showing that, well, the polarization, in principle, if you look at the whole system, then the polarization of lambdas is actually growing away from mid-repeativity. So the bottom part of the plot describes, shows the polarization of all lambdas, not only mid-repeativity, but all lambdas. And then, surprisingly, for all lambdas, the mean polarization is actually growing as a function of collision energy. And again, a little bit overstepping the topic of this talk. Let's say more broadly speaking, the same energy dependence trend is produced not only in hydro, but also in the non-hydro calculations, meaning transport model calculations. So practically what was done in those calculations is this method number one, which I was showing on one of the first slides. So there was an underlying transport evolution, which was coarse-grained at some moment of time. And then once it was coarse-grained, there was the same formula which was applied to compute the mean polarization of lambda and anti-lambda. So again, I hope that it will be discussed much more extensively next Monday. Now, moving on for the centrality dependence. So the two results which I which I scrapped and wanted to show is, again, from the URQMD plus VHLE on the left and PCR model on the right. So the general trend is that the mean polarization or global polarization is growing when you move from central to peripheral collisions. So on the left, you basically see the scatter plot of polarizations in the event by event hydrodynamics as a function of n part. So the smaller n part corresponds naturally to peripheral events, and you see that the average polarization is growing there. And on the right, there is a polarization done in, I think it's done in the in single shot hydrodynamics with fixed impact parameter. And here you can also see that okay, at lower energies, the polarization actually grows again from smaller impact parameter towards larger impact parameter. Now the ingredients of the models. So all of the models are naturally hydrodynamic models. First one is viscous hydrodynamic model. The other two are based on ideal hydrodynamics. So those models have different initial states. So in case of URQMD plus VHLE, unsurprisingly, that's URQMD initial state. In case of PCR, that's Young-Mills plus some sort of string picture. I mean, basically string model, which is evolved further with Young-Mills evolution, I suppose. In case of three fluid hydro, that's actually quite a bit different picture. So in case of three fluid dynamics, the initial state consists of two blobs of fluid. So it's kind of thermalized from T equals 0, and those two blobs of fluid, they collide. And because of the friction, the third fluid is created, which is baryon-free fluid, and it basically describes the production of mesons in the reaction. And and all of the fluids are ideal in this model. So the Cooper-Frye, I mean, the particularization is also done a bit differently in those models. So the first model does particularization fixed energy density. The second model does particularization at T equal either 6.25 or 7.25. I couldn't really figure this out from the publication. And the third model does particularization at, in principle, also at fixed Cartesian time, which is linked to the mean energy density, equal to 0.4 GeV per Fermi cube. So as you can see that the ingredients of the models are different a little bit. What is actually common and what is very essential is that all of the initial states, they have global angular momentum. Because without the global angular momentum, without this tilt, which creates the initial angular momentum, one cannot reproduce the global polarization. So the other particularity which I wanted to show is that, well, in the latter case, in the three fluid hydro, because there are three fluids and not one, there is a certain approximation which is used to compute the vorticity. So the approximation is that basically the vorticity of the overall local vorticity is a weighted sum of the vorticities of baryon fluid and meson fluid. So I don't really know how. I mean, I cannot really say or comment how good that approximation is. To me, it basically looks like a practical way to compute vorticity in the multi-fluid system. How good is that? Again, I don't know. Maybe Iurii can comment on that. But yeah, with that, I basically move to the next slide. So once you run the calculation and you see the energy dependence of polarization, there is a natural question. So what does the polarization correlate with? Meaning basically whether there is a correlation between polarization and angular momentum or something else. And in principle, let's say the simple answer to a simple question is no, it does not correlate, because early in this paper we have shown that, okay, naively the total angular momentum of the system, it grows with energy simply because of the collision energy factor. whereas the mean polarization, of course, decreases, the mean polarization of mid rapidity. And even if you scale that, if you scale the total angular momentum with energy, that still wouldn't decrease as much with collision energy. The other argument is that, okay, there is also the end part or centrality dependence of the angular momentum. And because of the overall geometry, the total angular momentum, it actually peaks at certain centrality, which is shown on the bottom left plot. And actually different from that, the mean polarization, it actually doesn't peak at certain centrality. It seems to steadily grow from central events to non-central events. So again, there is kind of no direct correspondence between the two. And actually much more extensive answer was given in the paper by Iurii Ivanov relatively recently. So they were also examining whether the global polarization correlates with angular momentum, the full angular momentum, or angular momentum at mid rapidity, or whether it correlates with directed flow or elliptic flow. And they actually found that the polarization observable itself, it pretty much does not correlate with any of those. So you see on the left plot that the polarization, the blue line, as you have seen on the previous slides, it steadily decreases with energy, but it doesn't change the sign. Whereas the directed flow, which is the dashed dotted red line, it actually changes sign. Same, actually, I'm not sure. Same seems to happen to the J, which is angular momentum, but I'm not sure actually what does it represent. But okay. So the conclusion which was drawn is that when it comes to mid rapidity, the polarization observable pretty much does not correlate with any of those. And I also, from the same paper, I also showed the other plot on the right, which sounded interesting to me, because here you can see the equation of state dependence actually. And what they found in the simulation is that the hydrodynamic evolution with hadronic equation of state, it even creates a negative, I mean, it even changes the sign of polarization at certain energy, which of course doesn't happen in experiment. So in principle, one can say that from this argument, the polarization observable more or less discriminates the hadronic equation of state. Though one can notice at this point that in principle in the earlier papers about the three-fluid hydro, the purely hadronic equation of state was kind of already discriminated from other more basic observables, but polarization observable seems to also disfavor the hadronic equation of state. Okay, so with that, I move towards the actual explanation of the energy dependence. So one of the explanation of the beam energy dependence of the global polarization is basically the following. So first off, you start doing the calculation different collision energy. The hydrodynamic system starts with different initial vorticity. So whereas at low energies there is a significant effect of baryon stopping, and the system is actually quite short in longitudinal rapidity. Then there is already shear flow, the so-called shear flow. So the shear of these white arrows, which you might see on the plot, which already exists at mid rapidity. Whereas at high energies, so on the right plot, you can see that at mid rapidity the system looks somewhat close to boost invariant. So because there is boost invariance, I mean there is approximate boost invariance, it does not leave a room for the shear flow, and that's why the initial vorticity at mid rapidity is very small at high energies. And then what happens next is that the hydrodynamic evolution itself, it actually dilutes, it actually suppresses the initial vorticity. So what you can see on those plots is the time evolution of the vorticity, or actually to be more precise, the distribution of local vorticities at the freeze-out hypersurface, which in case of freeze-out at fixed energy density, the freeze-out starts from very early and continues till the very end of the hydrodynamic evolution. So you see that in both cases at low energies on the left and at high energies on the right, the vorticity at the particularization hypersurface, it decreases with time. And then there is this argument that because the PT spectrum of lambdas, it decreases with PT, of course. So most of the lambdas are low PT lambdas. And the low PT lambdas, so lambdas with low transverse momentum, they are produced more probably at the end. So then at the end of the hydrodynamic evolution, you see that the vorticity at high energies is much smaller, also because the hydrodynamic evolution itself lasted longer. So it had more time to kind of dilute the initial vorticity which existed initially or early. It basically had more time to dilute it towards a very small value. And that basically explains the rather strong decrease of polarization from low energies to high energies. So that's the explanation from URQMD plus VHLE. I have to also list the explanations from two other models. So the PCR explanation has kind of two points. One point is that here I simply cite the sentence from the paper that from the thermodynamical perspective, the polarization decreases with energy because there is high temperature at higher energy of collisions. So this point I honestly don't really understand fully. The other point which explains the energy dependence of polarization is actually taken from AMPT calculation. So the argument which is drawn in this PCR paper is that, okay, if you run AMPT model, then one can actually show that the classical vorticity decreases with energy, and that leads to the decline of polarization. Though to me it sounds more like explanation not from the hydrodynamic model itself, but from some other model. And the explanation of the beam energy dependence from 3FD is basically in the same spirit as the first explanation from URQMD plus VHLE. So the points are the following: that overall the component, the omega zx, so the component of vorticity which is responsible for the global polarization, it generally decreases with beam energy because this vertical field is kind of pushed out to the fragmentation regions. So it is pushed out to regions of higher rapidity. Then there is also this other factor that at given beam energy, the vorticity decreases with time. So basically the same explanation as I was showing in the first place. And then there is also the next factor that the freeze-out time increases with beam energy, but actually only from small energies up to 27 GeV. So in principle, those two other factors they work against. They would actually increase the polarization with beam energy, but actually it turns out that the first factor actually dominates. So this kind of creates the overall decreasing trend of polarization with beam energy. But also the first bullet point, it also leads to this other effect that for the full system, so when one is not limited by mid rapidity, but actually looks at polarization of all lambdas from the fireball, then actually the polarization of all lambdas in the 3FD model, it actually grows with energy and not decreases. So, okay, the last point for this, for the global polarization is the robustness of the signal. So in principle, in the calculation with URQMD plus VHLE, we were asking ourselves a question that the parameters of the calculation, they depend on energy, on collision energy. So let's say the hydrodynamic starting time, the shear viscosity, it was taken to be dependent on the collision energy, and we wanted to basically check whether this collision energy dependence of other parameters is something which would modulate or create the trend for the polarization. And it turns out to be that it's actually not true. So the polarization is actually quite, I mean, the decreasing trend in the polarization with respect to collision energy is actually quite resilient with respect to the change in the model parameters. Or what you can see on the right is if you take average initial state or event by event initial state, or if you include the event time resolution, it basically all changes the results quantitatively, but not qualitatively. So qualitatively, there is always this decreasing trend, and it's very resilient with respect to the model parameters. So now I'll be slowly going to the local spin polarization. Actually, I'm already running mostly out of time. So basically on this slide, I wanted to show the point that, well, the overall trend of decreasing of the decrease of polarization with collision energy leads to the natural conclusion that at LHC energies there is probably no polarization which can be observed by the experiment, because the global spin polarization might simply fall out of the experimental sensitivity. So that's why already starting from early calculations, there were those plots, the quadruple structures, which were shown already in 2015 in the calculation with EcoQGP hydrodynamic code. I think at the time those quadruple structures went a bit, let's say, unnoticed. Then there was the other calculation by Long and Pan and collaborators, which was basically showing that in the case of event by event initial state, there are correlations of the longitudinal spins. So that's what you can see on the bottom right plot. Then further on, actually, the next finding was that actually those quadruple structures, especially the quadruple structure in the longitudinal polarization, so the plot on the bottom left, is actually quite general effect. So what we found is that this quadruple structure, it actually still emerges in the two-dimensional burst invariant hydrodynamics, and as such, essentially the only ingredient which you need for that is the asymmetric or azimuthally sensitive transverse expansion. So that's it for that. For this quadruple structure, you don't really need any angular momentum. You only need basically elliptic flow. Then, so to explain that, I basically throw this actually quite simplified and not quite accurate explanation, but well, you can catch the point from here. That so on the left you can see the sketch of the expanding system, and because you already see from this azimuthally kind of anisotropic expansion, it basically creates the velocity shear, and the velocity shear it modulates the vorticity exactly in this quadruple pattern. And because the polarization is proportional to the thermal vorticity, which is in turn proportional to the gradients of the velocity field, then this naturally emerges as a quadruple structure in the longitudinal polarization. So that's the oversimplified explanation of the effect, let's say. Because there is a quadruple structure, one can basically do Fourier expansion. So you can calculate the polarization at given modulus of transverse momentum and expand it in terms of the azimuthal angle. And then actually in the paper, which I will be citing on the next slide, it was found that this Fourier component, so the so-called F2, is actually proportional to the elliptic flow in the model. So that was a blast wave model calculation times the gradient of temperature with time. So that was a very simple formula which kind of links, in a simplified case, the amplitude of longitudinal polarization to the elliptic flow. So that's kind of very simple and elegant. And in principle, having this quadruple structure, one can do very simple exercise and compute the correlation of spins in the longitudinal direction, and the correlation which will of course follow the cosine 2 delta phi shape. So here I show the in principle unpublished results for how the correlation of spins would look like precisely from this quadruple structure on the right. So that's kind of very easy. The next thing which was shown is that, so because in the relativistic case, as I was saying, I mean, as was discussed already extensively, the polarization is, polarization is modulated by the thermal vorticity, which encodes both temperature gradients and flow velocity gradients. Then the thermal vorticity can be basically decomposed into the three parts. So the part which is proportional to the gradient of temperature, the part which is proportional to the so-called non-relativistic vorticity, which would reduce to non-relativistic vorticity in case of small velocities, and there is a last part which is basically proportional to the acceleration. And what we have shown is that so for the global polarization, we basically decomposed the global polarization and longitudinal polarization in the contributions from those three different parts. And what we have shown is that for the global polarization, the dominant part which plays a role is basically the vorticity. That's the dash dotted red curve on the left plot. And on the different from that, for the quadruple structure in the longitudinal polarization, actually the important and the dominant ingredients are the acceleration and gradient of temperature. And actually, in case of ideal hydrodynamics, one can show that those two contributions, they have to be exactly equal. So actually, the equality of those two contributions show that the hydrodynamic evolution is very close to ideal. So that kind of validates the overall, let's say, output of hydrodynamics. So that basically kind of confirms this expectation that the quadruple longitudinal polarization is basically dominated not by vorticity, but it's dominated by acceleration. In this case, azimutally anisotropic acceleration and also gradients of temperature at the moment of particularization. Now, with that, that this all looks very nice and comprehensive, but there is basically one problem, that the signal which we got in the hydrodynamic calculation had exactly opposite sign to the data. So this problem still kind of persists. So here I basically borrowed Francesco's talk from I think Quark Matter, the next to last Quark Matter. So there is already at the time there was a number of explanations which were kind of drafted to explain this difference in sign between the polarization in hydrodynamic model and longitudinal polarization experiment. And essentially after that, yeah.
Iurii, can you try to finish in a few minutes?
Yeah, sure.
Yeah. Okay. Thank you.
Yeah. So then basically the last things which I wanted to note is that there are a couple of calculations which actually show the opposite sign of the longitudinal quadruple structure. So one of such calculations is again the PCR, PICR. So in this recent paper, the authors simply state that they have opposite sign pattern for the longitudinal polarization. They seem to use the same formula, or I think so, actually, the same formula as other hydrodynamic calculations. So I'm quite actually unsure how they got this result. It's published in the paper, but I'm still not sure actually what does it all mean. The other explanation, the other result connected to this is the polarization in the thermal or blast wave model. So here what was proposed is that, okay, if you compute polarization according to the standard thermal vorticity, so on the left, then the sign is opposite to the experiment. But then if the polarization would be proportional to the so-called projected thermal vorticity, which is expressed on the bottom of the slide, then actually the polarization would flip the sign and would actually match the sign in the experiment. So how much is it? I mean, I'm also not sure whether basically how much is it really, how much of an explanation it is, but that's some interesting idea to discuss. And the last thing is that so also in the recent paper and also in the last group method there was a talk which was actually showing yet another idea that okay, if you compute polarization not only according to the thermal vorticity, so not only the red curve, which shows the opposite sign, but actually according to, if you try to compute polarization according to all four definitions of vorticity, then actually one of them, namely the so-called T vorticity, would actually produce the polarization pattern which has the same sign as an experiment. It is again not clear. I mean, this explanation probably creates more questions than it actually answers. But nevertheless, so that's what was stated in this paper. And actually, with that, I reached my conclusion. So, well, with the lack of time, I simply leave you at this slide. I mean, so the overall message is that when it comes to global polarization, the overall signal, at least when it comes to lambda, is more or less reproduced. There are feed-down contributions which will be discussed later in this workshop, but overall signal is basically reproduced. When it comes to local polarization, so generally in the hydrodynamic calculation, we see the patterns which are seen in the experiment, but actually there are puzzles. So the last bullet point actually lists two puzzles at least. So the first puzzle, the sign of longitudinal polarization, and I think the other puzzle is actually the angle dependence of the transverse polarization, which is also not quite captured in hydrodynamic calculations. So this basically leaves room for the further research, and with that I finish. So thank you for your attention, and now I'm open to questions.
Thank you very much for a very nice talk. So I think we still have a little bit time to take some questions. Anybody want to ask a question? I saw a few hands. So Chun Wang, please go ahead.
Yes. About the local polarization, it seemed that the temperature gradient part play some role, as we found. Let me, because we found that the T vorticity, if you choose the spin chemical potential as the T vorticity, then you do get the right trend and the magnitude. But that poses a question, because the T vorticity, the temperature contribution to the T vorticity and to the thermal vorticity just the opposite. So yeah. I think this is the problem. I think this feature that you get the can you get the your prediction correct? So I think maybe I would like to ask you, is it possible you reverse the temperature gradient on the boundary, for example, the freeze-out hypersurface? Is it possible to reverse the sign of the temperature gradient? If you have, I mean, if you have some kind of equation state that can make the gradient of the temperature inverse, then you can. I mean, can you be able to explain the data?
Well, I think it's not as easy, because in principle, at least when it comes to high energies and the signal is mostly discussed at high energies, it's basically the equation of state of baryon-free matter, and that's very well known from the lattice. So it's constrained by the lattice, and there we basically don't have any freedom. So you cannot, I mean, you can maybe construct the equation of state, actually quite weird one, where the temperature would decrease as a function of energy density in some region, but then that would be basically inconsistent with lattice QCD. So
Okay,
I don't think it's very easy to do that.
If this is impossible, then I think that maybe the T temperature, the T vorticity may be the key point to explain.
Sorry, Chair, may I comment? Just very quick
Okay.
comment.
Yeah. Of course, of course.
to go back, so that I mean, it's very hard to get the wrong sign for the gradient of temperature, because in the baryon-free matter, the ideal hydrodynamic predicts very clearly that the gradient of temperature is parallel to the acceleration with the same sign. So if you show your FT plot,
that's
you have two
basically
components. If you look at this acceleration and gradient of temperature as a function of PT, they almost overlap. This is an unmistakable sign that the hydrodynamics is quasi-ideal.
Yeah. You know the T temperature. People use the T temperature in the plasma physics for the ideal fluid. In ideal fluid, you can prove that the T temperature is conserved. Really, it's conserved.
Yes.
You mean T vorticity?
Yes.
But
T vorticity, not T. T vorticity.
Yes, it is conserved. Yes.
It's conserved. I mean.
Yes,
So,
can I also give a very quick comment on this point? Because
this is relevant to this. Okay, yeah, should go on, please. Yeah.
I think one point about the T vorticity is that it is roughly conserved in the fluid. Yeah, it is conserved in ideal fluid. If the viscosity is not large, it's roughly conserved. So it is like something like the spin, the fluid is flowing, so the spin is flowing with the fluid. So, and this makes T vorticity special than other vorticity. It's like some conserved quantity is flowing with the fluid, which means the curve that why we have the correct sign with the experiment may be explained by some conserved quantity which is flowing with the expansion of the system. That's I think later there will be a lot of discussion about spin hydrodynamics. So which means maybe later by using spin hydrodynamic simulation, we could see the similar behavior as the T, what show here for T vorticity.
So
okay.
I think this is the point. Yeah.
But maybe we can continue discussing this more later, but I think we have a few more hands. Let's take a few other questions for now. Wojtek, you want to ask your question?
So thank you. So Iurii, thank you for your nice presentation. I would like to make a comment on the calculations of us you showed.
Oh yeah, sure.
In the blast wave model on the left-hand side, we just confirmed in some sense what you did in sophisticated hydro. So somehow we get really the wrong sign. And so this is the blast wave, which gives us, B2 correct and the spectra. So I think it shows that somehow the blast wave model is consistent with hydro if the blast wave model is, describing the data. So this is the first point. I think the second figure on the right-hand side simply shows that if you use some different things, you can describe the data. Yeah. So somehow this is what Chunwan is saying, that somehow if you go away from thermal vorticity, probably you can describe the data. So for me, this is the sign that it's really, the spin degrees of freedom are not equilibrated. If the data are really correct, as we all assume as theoreticians, and if the theoretical calculations are correct, but they are very, very much consistent. Now, one comment about this thermal vorticity. This thermal vorticity and circulation is conserved only if the temperature is the only one thermodynamic independent variable in the system. And if you have baryon number different from 0, it's not conserved. So this argument that this is nice and beautiful quantity because it's conserved is not valid actually in the region when the polarization is measured. Yeah, because yeah, you have to have this, to prove that the circulation is conserved, you have to have something to be the, the gradient of some thermodynamic function. And this works if you have one independent thermodynamic variable, yeah.
Right. If going to lower energy, yes, maybe the biochemical potential
it's only
will be
valid
important.
in ultra relativistic regime when the polarization is zero anyway. Yeah.
Yes.
Okay,
That's
so
true.
we can discuss this more later. Thank you.
Thank you. So Hongwu, you want to ask a question?
Yeah, thanks. Could you go to slide 3, if you don't mind?
Sure. That's slide 3.
Yes. Yeah. So probably my question is related to the other questions just asked. So if you look at this definition of your spin, then it seems that it is perpendicular to the momentum 4 vector p sigma, right? So that it is purely special in the rest frame of the lambda particle. My question is, do you compute polarization in the rest frame of the lambda particle first and then convert to the left frame we are observing, or you first average this spin in the left frame, like what you have inside this box, then just compute this polarization somewhat naively in the left frame. So that's my question.
Yeah. So I think it's actually a very good question because it touched something which I left out on the slide. So in principle, yes, the polarization is so at a given momentum, the polarization is actually computed in the rest frame of the lambda, and then it's boosted to the global frame. I think that's the way it's done. Actually, Francesco can correct me if I'm wrong. So there is actually one transformation which is left out on the slide, but it's done.
I think it's the other way around. This formula predicts the Pauli-Lubansky vector, if you want, in the QGP frame. And then,
right.
In order to compare with experiments, this must be boosted back boosted to the lambda rest frame.
But lambda particle, different lambda particles have different momenta. So how could you just map from?
The fact you see that this is S mu as a function of P.
I mean, you basically you basically compute S mu at different momentum, and then you apply a Lorentz transformation at a given momentum, and then for the global polarization you average over the momentum at the end. So yeah, this is true. I now recall that an experiment actually one measures polarization in the rest frame of the lambda. So then we have to kind of do the reverse.
Can I ask just a very short follow-up question? So I think the important question is actually the definition of spin vector instead of actually spin 2 tensor, which I think is more fundamental. As far as I know, there are different definitions of spin vectors. Doesn't this result depend on some of this choice of what definition of spin vector you use, or it is more universal? Like the formula you have here in terms of summer vorticity and momentum. Is it kind of well defined without any ambiguity?
Actually, I mean, I would actually, Francesco, do you know precise answer to that?
Oh yeah. I think this question by Hong is very relevant for tomorrow's talks, as far as so I can invite people to follow tomorrow's talks to have, and especially Leonardo's talk in the morning. I think we'll make it this very clear.
Okay. Yeah. Yeah. Thanks very much.
I think the vector that you see here. And since I'm sorry that I'm talking again, because that is the only, say, it's the most proper relativistic spin vector defined through the Pauli-Lubanski vector. So it is quite universal. So it has solid foundations, I guess. I mean, I don't know if there is any other vector you can define.
I think it's consistent also with the definition through the density matrix. Yeah. So.
Yeah. This is the mean value of the Pauli-Lubanski operator. So.
Yeah, and this just is the mean polarization. If you measure the polarization, you will get the mean direction and the magnitude.
Yeah, it's the element of covariant density matrix.
Okay, so let's take the last question, Umut.
Yeah, I mean, of course, like my question is also going to have some overlap with the previous ones. So yeah, I was trying to understand what exactly are you evolving in these hydrodynamic evolutions. So energy momentum tensor and the spin density or spin vector, or just the energy momentum tensor, and then you calculate the spin density on top of that.
Exactly. Yeah. So that's the latter. Yes. So we only involve
the reaction of the spin flow is not really taken into account, and you would probably expect that this back reaction on the energy would be very small.
Exactly. Yes. I mean, there are. So what I understand is that back reaction can locally produce some differences for the local polarization. I mean, that's what probably Wojtek mentioned, or so that can have some effect on the local structures in the polarization. But for the global one, I mean, we basically, so all of the calculations which I'm showing here, all the classical hydrodynamic calculations, they only evolve the T mu. And then we apply this formula, this very formula, basically on top of that.
Yeah, I understand. But the T mu has an antisymmetric part, or
no. T mu is always symmetric. It doesn't have. We don't apply this definition of T mu. So.
And then it's kind of like, I mean, I'm confused about this Bill-Infante-Rosenfeld transformations, that you can always, change the T mu and the spin vector at the same time. So this expectation value, in some sense, would be dependent on the BR transformation, on the frame, some kind of pseudo gauge frame. So, I mean,
I think for now is what he talked about is all standard kind of hydro. I guess later in the week there will be discussion where you will treat the spin tensor.
I think Wojtek has this work about the different definitions of T mu and spin hydrodynamics as well.
Yeah, I mean, Kenji had a paper this morning that was also talking about PRs.
Okay, with that, I guess we should conclude this session and we take a short break. So let's thank Iurii again for a nice talk and for all the discussions we have here. I'm going to stop the recording.